So this now, like that was a different kind of issue, right? Whether R is complete or not, and so on. But if you assume that you have something like R ordered field and so on, which is complete, okay, it has a distance natural one, and with respect to that is complete. Then we would want to apply that to the following question: is completion of metric spaces. And then I would ask you to carry out the completion of non-linear spaces separately. Separately because you want the completion to also have an addition structure in the case of non-linear spaces, because they have an addition structure to begin with. But here that worry is not there. So yeah. So how do you complete a arbitrary metric space? That is a question. So of course, there was a construction which I was talking about last day. So yeah. So, yeah, let's see. So in this, first let me describe the problem. But I'm just sort of not last day, but last time. So, but let me describe the question. So, so basically you start with this, okay? And the problem is to construct a metric space, maybe you call it X prime, okay, with the metric D prime. Okay? So, say, given this, right, construct this such that this is complete. Okay? Yeah. Yeah, and right. So when I carry out this exercise, you should do this exercise concretely for, let's say, Q2. How do you go from Q2 to, how do you construct the completion of Q2? So obviously it will be R2, but you should do the construction. So you take Q2 and you want to complete it and get a metric space, which also has an addition structure, and yeah. So this is complete, and if you consider the, or maybe I should say that, and there is an inclusion, and not inclusion, but there is an injective function. There is a function I, which is from X to X prime, right? Which is from X to X prime, such that d of X comma Y is equal to d of Ix d prime of Ix comma Iy, right? So basically what I'm just saying is that you can think of X as a subset of X prime, right? So basically, if you look at X and instead consider Ix, yeah, take an element small x in X, and you instead instead of thinking of small x, you think of Ix, right? Then nothing changes. The metric completely remains the same. That's what this is saying. That is, Ix and Iy, they live inside X prime. They don't live inside X, but they behave exactly like X and Y would behave in X, in capital X. So Ix and Iy behave completely the same way in X prime as X and Y would behave in capital X. Right? So there is no distinction if you want to just think about them as metric spaces. Okay, that's what that property is saying. And Ix is dense. So this basically says that we don't want to, we want to just attach we want to consider X, we want to see which Cauchy sequences in X don't converge, and then we want to put those limits and nothing more. We want to do the minimal required construction. You see, correct, right? You want to do the minimal required construction. That's what this is saying, this condition, that the closure of this is X prime. Yeah. So you can check out this closure and then how it connects with dense subset, and it's just same thing, but you have to just read up those things, are basically basic metric space things. Okay. We want to do this construction. We want to do a construction which satisfies all these properties. Correct. However, there is one good nice thing that even if you don't know how to do this construction, you can do the following exercise. Even without doing the construction, you can do an exercise about this construction, about this X prime. Yeah. So basically, I want to say that the X prime is unique, there is only one X prime in some sense. What is that sense? The sense is quite a strong sense. If there is a I1, prove that, prove if I1 X double prime and D double prime satisfy the same properties as I, X prime, and D prime with respect to X and D, of course. Yeah. You see what I'm saying, right? If you replace everything here by, I1, I by I1, X prime by X double prime, and so on, and D by D double prime, then something happens. Then X double prime and X prime are homeomorphic, which means that you can construct a continuous function. You can construct a continuous function which is bijective, and also its inverse is also bijective. So this I will just write as X and X prime are isometrically isomorphic. You can check out this definition, but I have told you in a weaker way what this means. Okay. It's a very strong property. Okay. So this is one of the exercises about this abstract thing, meaning that you understand what it tries to say, but then to say it, it's a little complicated to begin with. I mean, once you get used to it, it will not be complicated. But you know what it is trying to do, okay? And the second is another property of this. So now you have proved that there is only one such thing, okay? And the second property is the following. If y is, if y comma d1 is complete, okay, then what happens? And if y comma d1 is complete, and we have the following: x to y, phi is a continuous map, a continuous function, right? Continuous function between metric spaces, from one metric space to another metric space. But the other one is complete. This is sort of formalizing this thing that it is the smallest, okay? And it is the smallest in a strong sense. Here it was smallest. Here it is smallest in one sense, right? A closure of this, but this doesn't mean smallest in every sense. For example, Q, a closure of Q is R. So R is the smallest construction with respect to Q, but still the cardinality of R is more than Q. So anyway, it depends on what smallest in what is your barometer. So what are you trying? How are you trying to compare it? In what dimension? Point here is that this x sits x to y, there is a continuous function. Well, phi is continuous function of metric spaces, which of course you know the intuition, but obviously we have packaged all that in this arrow. We don't have the time to say everything. I mean, that's inevitably what happens in mathematics. This thing, but then obviously this is already there always. This is always there, right? We have to show that there exists a function. What would you call it? Phi tilde. Yeah. So this thing, this happens. You just do this problem. Yeah. So given phi from x to y, yeah, show there exists a phi tilde from x prime to y prime, and of course you have to show it's continuous. Anything you construct, you have to show it's continuous, otherwise it's not interesting. But in metric spaces, the map should be continuous, at least continuous. Okay, so any function is sort of splitting through this I. Okay, that is the nice thing. Okay. Try them. Look, I'm not saying that they are simple, but you should try them, and we can build on these things. This is what is called a universal property of phi. This is sort of important, and yeah, all these things will show up everywhere when you do more other things. But then we have not done the main thing, is sort of how do you show that x prime exists? If it exists, it is sort of unique. It has a very, very nice, beautiful properties. I mean, mathematically beautiful in the sense that, very, very clean properties, but yeah. So yeah, so maybe we can do the construction next time, right? Yeah. So if you read up on this and if you think about these matters, try these problems, then see. Yeah. Next time we will, when we meet, we will. But yeah, prepare. I mean, about this complete metric spaces, you should do more and more problems, because then this abstract things will make sense to you. Of course, I mean, like constructing this function and showing that it is kind of, all these are exercises, right? But more and more you have to do. Yeah. Okay. Yeah. And yeah, about Rudin, the reference was the previous construction, which was a different kind of discussion. Probably I should have done them in different classes, but yeah, I mean, that is basically baby Rudin, the blue Rudin, principles of mathematical analysis, chapter 1, appendix. So that's in the appendix. It's not the main part of the chapter, but yeah, you can read the main chapter. You probably know most of that, but you all know that already. But yeah, you should read the appendix. That's where this construction is given, and there are some interesting remarks in the end which you should read. Okay. Yeah, so I think I'll stop there, and this is what we do. And in metric spaces, we will do many more things, and yeah, we would want to see, right, which metric spaces are complete really, and because completion can help you to also give a characterization of compactness. That also. Okay, I will stop here, and